All right, good afternoon. Let's get started. Last week we talked about chapter 1, and this week and the next we'll discuss chapter 2, which is very important. It's called probability. Okay, so this class name is the statistics and the probability. And chapter 2 is a pretty long chapter. I think we have close to 180 slides. Okay. So the next 2 weeks we'll discuss chapter 2. Today let's get the basic idea. First of all, what is experiment? Okay. So experiment is defined as a process that results in outcomes that cannot be predicted in advance with certainty. Okay. For example, we roll a die. Okay. So we could have 6 possible outcomes. 1, 2, 3, 4, 5, and 6. Okay, but we cannot predict in advance what value will come up. Or we toss a coin. In that experiment, we have 2 possible outcomes. We could have a head or tail. Okay, so head or tail. Okay, and we have 50% of chance get either head or tail. Right. Or we weigh the content of a box of cereal. Depending on weight, we may have a certain value. Okay. A sample space is defined as a set of all possible outcomes of an experiment. Okay. For example, rolling a die, a sample space is 1, 2, 3, 4, 5, and 6. Okay, so all the possible outcomes for the experiment of rolling a die is this 1, 2, 3, 4, 5, 6. Okay, or toss a coin. Okay, the sample space, all the possible outcomes is heads or tails. No other outcomes possible. Okay, or if we weight a cereal box, the sample space should be 0 gram to infinity. Okay. But for a box of 6-ounce cereal, the sample space may be somewhere between 12 to 20. Okay. So again, a sample space is defined as all possible outcomes for a certain experiment. An event is a subset of a sample space. Okay, the basic element to which probability is applied, and when an experiment is performed, a particular event either happens or it doesn't happen. Okay, for any sample space, we also have a so-called empty set. Okay, which is nothing happened, and also the entire sample space. Okay, entire space is also an event. So does empty space. Empty set. And a given event is said to occur if the outcome of experiment is one of the outcomes in the event. Okay, so go back to the rolling a die experiment. If the dice come up with a 2, then the event of even number, which including 2, 4, and 6, so that event occurs. And also the event of we have number less than 4, which including 1, 2, and 3. So the event of have number less than 4 also occurs. Okay, so both of these 2 events occurs when the dice come up with number 2. Okay, and also every other event that contain outcome with 2. For example, for number less than 5. Okay, so that event also occurs when the dice comes up with 2. Okay. Right. So another example of experiment. Okay, for example, we record the age of person. Right. So event A, let's say person is 30 years old, or event B can be defined as person is older than 65. Okay, so that's another example of events. And for the experiment of toss a die, event A can be defined, for example, observe an odd number, which including 1, 3, and 5, or event B, observe a number greater than 2. In that case, will be 3, 4, 5, and 6. Okay, so that it will be another event greater than 2. All right. And here is another example. Let's read it together. Electrical engineer has on hand 2 boxes of resistors. So empty set, so I got a question from Kira. So empty set means in that event, there's nothing happens. Okay, nothing in it. Okay, so sample space is the opposite of empty set. Sample space include all the possible outcomes for that experiment. Okay. Okay, go back to the example of resistors. So we have 2 boxes of resistors. Okay, with 4 resistors in each box. Okay, so the resistor in the first box labeled 10 ohms. Okay, but in fact, the actual resistance are 9, 10, 11, and 12. Okay, so in the first box, we have 2 resistors. For the second resistors, which is labeled 20 ohms, but in fact, the resistance are 18, 19, 20, and 21 ohms. Okay, so the engineers choose 1 resistor from each of these 2 boxes. Okay, so this example is pretty straightforward. Then let's look at, say, let's define A is the event that the first resistor has resistance greater than 10, and event B is the second resistor has resistance less than 19. Okay, and event C is the sum of the resistance is equal to 28. Okay, so let's find out what are the event in event A, B, and C. Okay, so first of all, let's find the sample space. The sample space again is all the possible outcomes. Okay, so based on the counting method, here is the sample space. Okay, so we pick 1 from each of these 2 boxes. For box number 1, we have 4 resistors. So we have 4 possible picks. Okay, and for the second box, we also have 4 possible picks because we have 4 resistors in the second box. So the total sample space should be 4 times 4, which is 16. Okay, we'll talk about counting method later in chapter 2, but here is the sample space. Okay, okay, including 9, 18, 9, 19, 9, 20, 9, 21. So that's for the first box, the resistor is 9. Okay, and so on, we have this remaining 12 possible outcomes. Okay, so let me write down why the sample space is like this. Okay. All right, so yeah, I hope you can see my iPad. So we have 2 boxes, right? So the first box, we have, so box number 1, we have 4 resistors, 9, 10, 11, and 12. Okay. And box number 2, we have 18, 19, 20, 21. 20 and 21. Okay, so for this experiment, how we can find the sample space? So let's see, the first step, we pick 1 from box number 1. If the first one is 9, then we could have 9, 18, 919, 920, and 921. Okay. If the first peak is 10, then we have 1018, 1019, 1020, and 1021, and so on for 11 and 12. So that is totally 16 possible outcomes, like we can see from the sample space. Okay. And then let's look at event A, which is defined as the first resistor has resistance greater than 10. Okay, so greater than 10, which means the resistor in the box number 1 could be 11 or 12. Okay, so for 11, it could be 11, 18, 11, 19, 11, 20, and 11, 21. For 12, we have 12, 18, 12, 19, 12, 20, and 12, 21. Okay, so we have totally 8 possible outcomes for event A. Okay, so we call that counting method. We count what are the possible outcomes. B, event B is defined as the second resistor has resistance less than 19. Okay, so less than 19, only 18 is possible. Okay, so we could have 918, okay, or 1018, or 1118, or 1218. Okay, so that is event B has 4 possible outcomes. All right, and event C is event that the sum is 28. Okay, so how to do that? We just go back to the sample space. We add 2 resistors together and find out which one is equal to 28. So turned out we have 2 of them. 9 plus 19 is 28, and 10 plus 18 is also 28. No more. Okay, so this is how we can get the events. All right. Okay, so let's go back to the event, the experiment of rolling a die. Okay, so event again is outcome of experiment. Okay, so to toss the die, let's see what number are in on the top surface. Let's say event A is defined as we observe an odd number, so that including 1, 3, and 5. Event B is number less than 3. Okay, so which including 1 and 2. Okay, so that's event B. So both event occurs when the upper face shows a 1. Okay, so when we have 1, that means we observe an odd number, so event A occurs. And also event B occurs because 1 is less than 3, right? Okay. And then these are the simple events. Okay, observe 1 or 2 or 3, blah blah to 6. Okay. Two events are called mutually exclusive if when one event occurs, the other one cannot occur, and vice versa. For example, for event of odd number, if that event odd number occurs, then the event of even number cannot occur. Okay, so that's the example of mutually exclusive events. And event A and B can be further decomposed into simpler events. Okay, so event A is odd number. Odd number, we can further decompose that into we get 1, or we get 3, or we get 5. Okay, and event B, which is we get number less than 3, can be further decomposed into E1, which is we get 1, or E2, we get number 2. Okay, so simple enough. Okay. An event that cannot be decomposed is called simple event. Okay, for example, E1. we get number 1. So that is a simple event because it cannot be further decomposed to even simpler events. Okay. And a set of all mutually exclusive simple events is a sample space. Okay. For the example of toss the die, the sample space will be 1, 2, 3, 4, 5, and 6. Okay, so these are the 6 simple events in the experimental toss the die. Okay. And the event is a collection of one or more simple events. For example, event A, all number, we have 1, 3, and 5. We have 3 simple events, and so on. Okay. All right. So the simple events again will be E1, E2, E3, E4, E5, and E6, and the sample space will be S. Okay, S is for sample space, including all the simple events listed here. Okay, sometimes we can also draw a figure here. S is the sample space, simple events is inside. All right, so let's look at die toss experiment again. Okay. An event is a collection of one or more simple events. And remember, we have 2 events, A and B. So A is we have odd number. And we can see here, for odd number, we have E1, E3, and E5 in that circle A. So circle A is event odd number. Okay. And event B is we have number larger than 2, which includes E3, E4, E5, and E6. Okay, so that's event B. And we can see here both E3 and E5 include in event A and event B. Okay, so that gives us a new idea, which is union. Okay, the union of 2 events, A and B, which we can also write as A with half circle facing up. This is called A or B. Okay, A or B is a set of outcomes that belong either to A, to B, or to both. Okay, so we also call that A or B. So event A or B occurs whenever either A or B or both occurs. Okay, so go back to the previous slides. Okay, event A or B including E1, E3, E5, E4, and E6. Okay, so 5 simple events. Okay, any one of these 5 events occurs, event A or B occurs. Okay, so we call that union. Okay. Another example, event A 1, 2, 3, and event B is 2, 3, and 4. So what is A or B, or union of A and B? Okay, we're gonna write all the events in A and B. Okay, but remember to not repeat. Okay, so A or B will be 1, 2, 3, and 4. Okay, remember to not write 2 twice and do not write 3 twice. So A or B will be again 1, 2, 3, and 4. Okay, so that is called union. Intersection is different from union, it's opposite of union. So intersection of 2 events and B, we write as A with a half circle facing down. Okay, we call A and B. Okay, is set of outcomes that belong both to A and B. Okay, remember that two circles of A and B, that is event within that intersection of that two circles. Okay, so the event A and B occurs whenever both A and B occurs. Okay. Right. If event A is 1, 2, 3 and B is 2, 3, 4, what is A and B? Okay, so both A and B occurs when we have 2 or we have 3, right? So both event A and event B has number 2 and number 3. So A and B will be event including 2 and 3. Okay. Go back to that example. Okay. So A and B will be E3 and E5. Okay. So this is the shaded areas which including both circle A and circle B. So this is intersection of A and B, or we call that A and B. So inside it we have E3 and E5. So A and B equal to E3 and E5. Okay. Any questions so far about intersection and union? Okay, so these two are very important concepts. Okay. All right. Yes. No, A and B doesn't have to be a simple events. Simple events, just events cannot be further decomposed to simpler events. For example, 1, toss a die, we get a 1. So 1 is a simple event. But A and B are not simple events, right? So A has 1, 2, 3, have 3 simple events. And B has 2, 3, 4, also have 3 simple events. Okay. All right. Okay. Yeah. So A and B means, the events when both A and B occurs. And A or B defined as either A or B or both occurs. Okay. Go back to this graph. Okay, so for example, event A is 1, 3, 5, and B is 3, 4, 5, and 6, as we see from here. So A or B will include E1, E3, E5, E4, and E6. So anything within circle A and circle B. On the other hand, A and B, which is the intersection of circle A and circle B, so that is both A and B occurs. So that including E3 and E5. Okay. And we can see E2 is outside circle A and circle B. Okay, and we're going to talk about that in a moment. So complement of event A, which can also be read as A with a C on top, C is for complement, is the set of outcomes that do not belong to A. Okay, so AC means not A, so the event not A occurs whenever A does not occurs. Okay. So if we draw a 5, 6 side die, okay, and event A is defined as we rolling a 6, okay, so this is event A, then complement of C, not rolling a 6, is what? is the other possible outcomes, which is 1, 2, 3, 4, and 5. Okay. Two events, A and B, are said to be mutually exclusive if they have no outcomes in common. Okay, which means the intersection of A and B. Okay, P is for probability. The probability of intersection of A and B is equal to 0. There's nothing in common of these two circles. These two circles does not touch. Okay, then we call that two events mutually exclusive. Okay. If you have more than two events, A1, A2, AN, then it's said to be mutually exclusive if no two of the events has any outcomes in common. Okay. That another name for mutually exclusive events is called disjoint events. Okay, nothing in common, no intersection, or P, A, and B equal to 0. Okay. For example, okay, again, toss the die. Event A is we have odd number. Okay, event B is we observe a number greater than 2. Okay, so event A and B mutually exclusive. Okay, so all numbers including 1, 3, and 5. Greater than 2 including 3, 4, 5, and 6. Okay, so these two events have something in common. For example, 3 and 5. If you get 3, event A occurs. Right? This is odd number. Also B occurs, event B occurs. 3 is larger than 2. Okay, so A and B have something in common, so they are not mutually exclusive. Right? How about event C and D? Event C is we observe a 6, and event D is we observe a 3. Event C and D mutually exclusive? Yes. Right? So if we observe 6, we cannot observe 3 for a normal die, and so on. So event C and D are mutually exclusive. How about event B and C? Okay, so event B is greater than 2, so that's 3, 4, 5, 6. And event C is 6. So event B and C, does they have something in common? Yes, 6. Okay, if 6 happens, that belongs to event C and event B. So B and C are not mutually exclusive. How about B and D? Okay, B is 3, 4, 5, 6. D is 3. Okay, so if we have 3 observed, then D occurs, and also B occurs. Right? So B and D are not mutually exclusive. All right, then let's go back to register example. Okay, here are the questions. Is it possible for event A and B both to occur? Okay, how about B and C, A and C, and which pair of events are mutually exclusive? Okay, so then let's go back to the questions. Okay. So that is event A. Okay. So event A, by the way, is defined as the event that the first register has a resistance greater than 10. Okay, greater than 10. So this is, we have A possible outcomes for event A. Okay, so event B is event that the second resistor has resistance less than 19. Okay, so we have 4 possible outcomes. Event C is the sum of the resistance is equal to 28, so we have 2 possible outcomes. So that's events A, B, and C. Okay. Okay. So we can first write what is A or B. Again, this is A or B, which is half circle facing up. We also call union of A and B. That means whenever A occurs or B occurs, or A and B both occurs, that is anything within that 2 circles of A and B. So that is union, okay, or A or B. Okay, so we can just put event in A and event in B together. Okay, but remember, do not repeat the same events. Okay, if they have something in common, do not repeat. For example, 12 and 18, okay, they occurs in A and B. When you do copy, do not repeat this. It just occurs once. Okay. And so on. We can also write what is A and B. Half circle facing down is A and B. That means when both A and B occurs. So anything in common of A and B, we should put here. Okay, 11, 18. So 11, 18 occurs in both B and A, and so does 12 and 18. 12 and 18. Okay, so that's A and B. Then go back to the previous question. So is it possible for event and B both to occurs? We just check, if there's anything in common for event A and B. In fact, yes, we have 11, 18 and 12, 18. Okay, 11, 18 and 12, 18. Okay, they have something in common. Okay, how about B and C? Okay, does B and C has anything in common? Okay, we just check anything in common between B and C, and the answer is also yes. Okay, we have 10, 18 and occurs in both B and C, and so on. Okay, so I will just skip the remaining 2 questions here. Right, and we write what is A and B and what is A or B. This is A or B. This is A and B. We can also write what is union of B and C. Union is also called B or C. Anything in B or C or both A and C. Okay, so we put event in B and event in C here. But again, do not repeat. Do not repeat. Okay, so if the internet connection is not as good, don't worry. I will upload the video to YouTube, so you can review that. So what is B and C? Okay, B and C occurs in both B and C is 10, 18. Okay, no more. How about A and C? This is A or C, half circle facing up. Okay, anything in A or in C or in both A and C should appear here. But again, do not repeat simple events. And A and C. Okay, let's look at A and C. Is there anything in common between A and C? Okay, 919 in C but not in A, 1018 in C but also not in A. So A and C has nothing in common. So we call that empty set. Okay, they have nothing in common or none. All right. Okay, so let's continue. Before we do that, any questions about intersection and union? Okay. So probability, each event in the sample space has a certain probability of occurring. Okay, and probability is quantitative measure of how likely the event is to occur. Okay, and we write the probability as PA. P is for probability. So probability of event A occurs is right like this, PA. Okay, and PA is the proportion of times that event A would occur in the long run if we repeat the experiment over and over and over again. Okay. So let's see if we perform an experiment n times. The relative frequency of event A is defined as the number of event A occurs. Let's say this number equal to k divided by the number of event experiment performed, which is n. Okay, so k over n is the relative frequency. Okay, and the probability of event A is defined as when the n approach infinite. Okay, when n approach infinite number, this is probability event A occur.
Sorry, you're starting to break up, Professor.
Okay. Yeah, sorry, maybe my internet connection is not as good, but again, I will upload the video to to YouTube. You will get the link from Lolima, if you miss anything from class. Okay, sorry about that. Okay, so PA, probability of event A, is defined as when n approach infinite. Okay, that is k over n when n approach infinite. And because PA is a probability, and the probability is a number between 0 and 1. The smallest is 0%. The largest possible is 100%. Okay, so between 0 and 1 inclusive. And event A can never occur, then we call it PA equal to 0. Okay. If event A always occurs, then the PA is 1 or 100%. All right. And the sum of probability of all simple events in S is the sample space, okay, always equal to 1. Okay, again, what is simple events? Simple events is the event cannot be further decomposed into simpler events. Okay, so all the simple events added together is equal to 1 or 100%. Okay, and the probability of event A is found by adding the probability of all the simple events contained in A. So give you an example. Toss the die. What is the probability we get an odd number? The probability we got an odd number, by intuition we know it is 50%. But how we can get there? Okay, so odd number including the probability we got we got 1, and the probability we get 3, and the probability we get 5. Okay, so the probability we get odd number is equal to the probability we get 1 plus we get 3 plus we get 5. Okay, and what are the probability we get 1? And by intuition, okay, we have 6 possible outcomes. Okay, and the probability we get a 1 is 1 over 6. Okay, and so does the probability we get a 3, also 1 over 6. So 1 over 6 plus 1 over 6 plus 1 over 6 is 3 over 6, is 50%. So the chance we get odd number is 50%. Alright, so this is axiom of probability. So axiom means universally accepted principles. Okay, so it's always, you can always think this to be true. If S is a sample space, then the probability of the sample space is equal to 100%. Okay, and for any event, the probability is less or equal to 0 and larger or equal to 0, sorry, and less to equal to 100%. Okay. If A and B are mutually exclusive events, okay, then the probability of A or B, again, the half circle facing up, we call that union of A and B, or A or B. Okay, if these two events are mutually exclusive, then probability of A or B is equal to PA plus PB. Okay, and if we have more than two events, then the probability of A1 or A2 or A3 is equal to the probability of A1, A2, A3 added together, provided they are mutually exclusive events, which means they have nothing in common. So what about if we have something in common? Then the equation will be a little bit different. We're going to see that in a moment. The L is just A1, A2, A3. Doesn't really mean anything. Just means we have more than two events. Okay, so L means A3, A4, A5, AN. Okay. All right. All right. For any events A, AC is complement of A. Okay, the probability of complement of A, remember, complement of A is also called not A, which means PAC is the probability of A not occurs. It is of course equal to 100% minus the probability A occurs. Or if we put PA to the left side, which tells us the probability of A occurs plus the probability of A not occurs is equal to 100%, of course, right? And let's denote empty set, which means nothing occurs. Then the probability of empty set is equal to 0. Okay. And if A is an event containing outcomes O1, O2 as okay, here just means O2, O3, O4, and On. Okay, I don't know why my internet connection today is not very good. Again, very sorry. If A is the event of O1, O2, and On, and then PA is equal to PO1 plus PO2 plus PO3 plus PON. Okay, so this is outcomes. Okay. For example, the event, we get odd number. So odd number including outcomes of 1, 3, and 5. So the probability of we get odd number is equal to P1, the probability we get 1, plus P3 plus P5. All right. Sample space with equally likely outcomes. This is the case we meet most common. Okay. There's many situations that the sample space with equally likely outcomes can be constructed. For example, toss the die, toss a coin, do the lottery. So these are examples of equally likely outcomes. Okay. A particularly important case is such as the random selection of items from a given population. Right. Okay. So if a sample item is a sample at random, it can be thought as a sample space with equally likely outcomes. Okay. So let's say S is a sample space. And within the sample space, we have n equally likely outcomes. Okay. And if event A containing k outcomes, then P event A is equal to k over n. Okay. Again, one example of that is P odd number. Okay. So P odd number including 3 possible outcomes, 1, 3, and 5. Okay. The sample space has 6 total possible outcomes. 1, 2, 3, 4, 5, 6. Okay. So as a result, the probability we get odd number is equal to 3 over the total possible outcomes, which is 6. So 3 over 6 is 50%. So the probability we get odd number is 50%. Okay. So this is example of equally likely outcomes. Let's look at another example. Okay. So extrusion die is used to produce aluminum rods. Okay. And then we have specs for the length and the diameter of the rods. Okay. For each rod, the length can be classified as too short, too long, or okay. And for diameter, we can also classify as too thin, too thick, or okay. Okay. And for 1000 rod, we do the categories for each class, as in this table. For example, we have 900 rods, both the diameter and the length are okay. All right. So question, if a rod is sampled at random from this population, what is probability that it is too short? Okay, so these 1000 rods are equally likely events. So we just count how many rods in each class. Okay, so the probability that is too short, okay, so too short is here, including it is too short, too thin, we have 10 of them. Too short, okay, we have 3 of them. And too short, too thick, we have 5 of them. Okay, so what is probability the rod is too short? Okay, so the answer is, how many rods are too short? So that is 10 plus 3 plus 5. Okay, so 10 plus 3 plus 5 is equal to 18. So 18 divided by the total number of rods, which is 1000. That is the probability the rod is too short. Make sense? Okay, again, the probability is too short is 10 plus 3 plus 5 divided by 1000. Okay. So if A is an event containing outcomes O1, O2, O3. Here K again means O2, O3, O4, blah blah, and On. Okay. Then the probability of A is equal to PO1 plus PO2 plus PON. Okay. We just discussed if A and B are mutually exclusive. If they have nothing in common, then P or B, PA or B is equal to PA plus PB. Okay, we just talked about that moments ago. What if A and B are not mutually exclusive? Okay, then we should use this equation. So PA or B is equal to PA plus PB minus P. This is PA and B. So half circle facing down is and. Okay. So go back to the rod questions. If a rod is sampled at random, what is the probability that it is either too short or too thick, or both? Okay, so this is asking the probability is P too short or P too thick. Okay, so P too short including, as we just discussed, 10 plus 3 plus 5 divided by 1,000. Okay. Similarly, P too thick is equal to these three added together divided by 1,000. So that is the probability is too thick is equal to 5 plus 4 plus 13 divided by 1,000. Okay, but based on the equation we just discussed, we need to minus the intersection of these two events. Okay, P, A, and B. What is the intersection? The intersection of P too short and too thick is here, 5. Okay, so we have 5 rods which is both too short and too thick. Okay, so that means we need to use the equation of the probability is too short or too thick is equal to the probability is too short plus the probability is too thick minus the probability is both too short and too thick. Okay, I know it's kind of hard. Let me draw something here. All right. Do a new share of my iPad. Okay. So for the rods, no, sorry, it's here. Yeah, here. So the property is too short is 10 plus 3 plus 5 divided by 1,000. Okay. So we can write here, if we define A is the property is too short, okay, and B, this is it is too thick. Okay, so for these two events, they have something in common. Okay, what do they have something in common? This. Okay, we have 5 rods which is both too short and too thick. So where we should put this 5? So we should put this 5 in the intersection here. Okay, so that means these 5 belong to both A and B, belong to both too short and too thick. And for too short, we have 10 plus 3. Okay, so 10 is here, too short, too thin, and too short, okay. And similarly, for too thick, we have 4 plus 13. 4 plus 13 here. All right. So to calculate the probability is too short or too thick or both, we can use PA plus PB minus PA and B. Okay, and PA is 10 plus 3 plus 5 divided by 1,000. Right? And PB is 4 plus 3 plus 5 divided by 1,000. Okay, and don't forget we need to minus PA and B. This is the 5. So minus 5 divided by 1,000. And from this diagram, we can see clearly why we need to minus this PA and B. Because PA, we add 10, 3, and 5. Okay? And for PB, we add 4, 13, and 5 again. So we add 5 twice. Okay? This is not fair. It's not right. So that's why we need to minus that 5 once. Okay? So we count 5 only once to offset that. So remember, if A and B has something in common, we should use this equation. Okay, PA or B is equal to PA plus PB minus PA and B. All right, let's have another example. So a target on test firing range consists of bullseye, okay, with 2 concentric rings around it. Okay, so a projectile is fired at target. Probability that it hit the bullseye. Let me draw something here. Okay, so let's say this is the bullseye. So this is bullseye. Here the bullseye is 0.1 or 10%. Okay. The probability that hit the inner ring is this part. Okay. So between the first and second circle, the probability to hit the inner ring is 0.25, okay, which means it hit this area is 0.25. And the probability hit the outer ring is this area, is 0.45. Okay. So what is probability the projectile hit the target? So hit the target means it hit anywhere on the big circle, the big pie. So pretty simple. The P hit target will be probability hit bullseye plus the probability hit the inner ring plus the probability hit the outer ring. Okay, because this is the ring, okay, that's not including the bullseye. So we can just simply add the probability together. 0.1 plus 0.25 plus 0.45. Okay, so this is 0.8. Okay, because these 3 events, hit the bullseye, hit the inner ring, and hit the outer ring, are mutually exclusive events. See, they have nothing in common. Remember, this is the ring. The ring does not include the bullseye. Okay, so we just add this probability together. Second part, what is probability that it meets the target? All right. So it meets the target. Okay, is just equal to, we can see the probability to hit the target not hit the target, or C, PC hit target. C is for complement. Okay, this is equal to P1 minus P hit the target is equal to 1 minus 0.8. Okay, so that is 20%. Okay. All right. Another example. Okay. A process that manufactures aluminum cans. So the probability a can has a flaw on its side is 2%. And the probability it has a flaw on the top 3%. And the probability that the can has a flaw on both the side and the top is 1%. Okay. So the flaw could happen on the top or the side. Okay. Sometimes it occurs on both. So the question is asking, what is the probability that a randomly chosen can has a flaw? Okay. So because these two events, which are flaw on the side and flaw on the top, are not mutually exclusive events. So we should use the equation we just discussed. So F is for flaw, the probability it has flaw is equal to the probability has the flaw on the side, Fs, plus the probability has a flaw on the top, Ft, minus the probability has a flaw on both the side and the top. So Fs and Ft. Okay, so remember when two events are not mutually exclusive, they have something in common. They have intersection. We should use this equation. Right. So plug in the number. Probability has flaw on the side, 0.02. Probability has flaw on the top, 0.03. Okay, minus the probability has a side and on the top, also given us 0.01. Okay, so that is 4% of chance it has a flaw on. It has a flaw. Okay, and if we draw a diagram like this, okay, so we could see we have two circles. One is for flaw on the side. The other is we see flaw on the top. Okay, then the intersection is flaw on both top and side, which is 0.01. Okay, and from there we can also figure out what is probability it has flaw on the side but not on the top. So for example, this area, then this area will be the probability has flaw on the side, which is 0.02, okay, minus it has flaw on both sides and the top, minus 0.01. And similarly, for these areas, which is it has a flaw on the top but not on the side, so this part is equal to 0.03 minus the intersection, 0.01. Okay, so we're going to discuss this more. Let's continue. What is probability that it has no flaw? Okay, the probability has no flaw is the probability it has no flaw. FC means complement of has no flaw. So that is equal to the probability it has flaw, which we just calculate 4%. So 96% a can has no flaw. All right, we're almost there for today. Okay, so this question is asking, again, the same question. What is the probability the can has a floor on the top, okay, but not on the side? Okay, so let's see, FT means floor on the top, right? FS means floor on the side. Okay, and intersection part is it has a floor on the top and on the side, right? So the question is asking, it has a floor on the top but not on its side. So which areas the question is asking? On the top but not on the side. Okay, so it should be this area. On the top but not on the side. So that's not including the intersection. So this area is the question asking. Okay. So the floor on the top is equal to, it has a floor on the top and a floor on the side, then which is this part, plus it has a floor on the top but not has a floor on the side. Remember, C is for complement. This is no floor on the side, which is this part, this area. Okay. And from the question tells us it has a floor on the top, 3%, has floor on the top and the side is 1%. So from there, we can calculate, just plug in the number. So this is 0.03, right? And this is 0.01, and this is 0.3, 0.03 minus 0.01. So that is 2%. Okay, so today we talk about probability, and it can be found using based on empirical study, okay, or common sense based on mutually likely events. Like we know already, we toss the die, the chance we get 1 is 1/6. We toss the coin, the chance we get a head is 50%. Okay, why it is this based on equally likely events. Okay, if we toss the coin is fair coin twice, what is the probability that observing at least one head? Okay, this question is a bit more complicated. So we toss the coin twice. Okay, so the first thing we need to do is we need to figure out what are the possible outcomes. Okay, we should think this experiment, we should decompose this experiment into steps. We toss the coin twice. So the first step is toss the coin once. Okay, so the possibility is we get head, we get tail. So we have 50-50 chance we get head or tail. Then for the second coin, if the first coin we get head, the second we can also have head or tail, right? So we have head or head tail. If the first toss we get tail, then the second toss we also get head or tail. So we have tail, head, and tail, tail. So these four are all the possible outcomes of toss the coin twice. Okay, and because they are equally likely events, each of these four events we have 25%, 1/4. So the probability we have at least one head, we can just count head means H, right? Here has two head. One head, no head. Okay, out of these four, three of them has at least one head. So we just add the chance together. Equal to PE1, which is head, PE2, which is head-tail, PE3, which is tail-head. So 3/4. Okay, so this is an example of a counting method, which we're going to discuss next class. Okay. All right, so we have 2 more minutes and we have 2 more slides for section 2.1. Okay, so a bowl has 3 M&Ms, 1 red, 1 blue, and 1 green. A child selects 2 M&Ms and random, asking the probability at least 1 is red. Again, we do the so-called counting method. For the first pick of candy, we could have red, blue, or green. Right? And for second pick, let's look at, if the first pick is red, we have blue and green remaining. Okay, so the second M&M can only be either blue or green, cannot be red anymore. Okay, so blue and green. And same thing for the first pick is blue and first pick is green. Okay, so these are the possible outcomes. How many? We have 6. We have red, blue, red, green, red, blue, red, blue, green, green, blue, green, red. And they are equally likely events. Everyone has 1/6 chance. So at least 1 red, again, we just count. Okay, equal to P red, blue, P blue, red, red, green, green, red. Okay, so 4/6, that's 3/3 chance. We have at least red. All right. So in summary, if a simple events on experiment are equally likely, like in the M&M candy, you toss the coin, dice, then we can calculate the probability of event A just as NA/N. So NA is number of simple events in the A, and N is the total number of simple events. So we call that counting method or counting rule. All right, so that's the end for section 2.1, and Thursday this week we're gonna continue for section 2.2, which is counting method. Very interesting.